I will say, unification of IMARC as well as INCAP, which we were discussing. So in this particular conference, now we are going to have from December 12th to 16th, 2022, and all the domains of antennas, microwaves, as well as propagation we are going to cover. And we expect that this is going to be on the similar lines of European Microwave Conference, and more than 1,000 delegates will be participating. Our aim is to have at least 500 plus papers, and we are also planning to organize a trade show, because we are with the form of paper presentations, talks, and other things. We will know about the theoretical advancement, what is happening in antenna, microwave, and propagation, but product wise and in the simulation software, what kind of advancement is happening in this field. It is very easy to just go roam around to those exhibits, and we will get a very nice and wonderful ideas as well as update about what is happening in industry, which is also important for anyone's professional growth. So there also we are trying to have one of the largest industry participation, 50 plus industries we are aiming right now that we will be having their exhibit booth. So with this small introduction about MapCon, I invite all the participants to be ready with paper presentation, with paper submissions, because we are going to open our paper submission portal on April 15th. And again, we have taken a new initiative that we are not going to have a early registration offer, because I don't see any value addition with early registration except getting money early. What we want to make the life simple of TPC and have quality reviews from the TPC. We have introduced a concept of early submission, where if you are submitting your papers early, then you will be benefited, and we will be giving you a discounted registration fee over and above regular registration fees. So that is the concept we are talking about. So be ready with paper. That's why I am telling, if you are submitting your paper within the first month of the opening of this paper submission, then you are going to be benefited hugely. Numbers and other things one can see on our website as well as brochure. So with this pitch about IEEE MapCon, now I will leave the floor and welcome again Dr. Nasimuddin and Dr. Kedar as well as Mahesh. Over to you. Thank you.
Thank you very much, sir. Thank you very much for your words and introducing the MapCon, this thing. Thank you very much. And yeah, now I hand over the floor to Dr. Ashutosh Kedar, sir, to introduce the speaker and to start the event. Thank you.
Thank you, Mahesh. Good evening to all and good night to people who are having the night at this time. So Dr. Nasimuddin received his BSc in 94 from Jamia Millia, India, and his MTech and PhDs in 1998 and 2004 from University of Delhi, India. He has worked as a senior research fellow in DST project and CSIR grant as a SRF in engineering science for the project investigations of microstrip antennas as a sensor for determination of a complex dielectric constant of materials at Department of Electronic Science, University of Delhi. He has worked as an Australian postdoc research fellow from 2004 to 6 and was awarded a discovery project grant from Australian Research Council for a project microwave sensor based on multi-layered microstrip patch-line resonators at Macquarie University, Australia. Currently, he is working as a scientist 3 at the Institute for Infocomm Research A*, Singapore, and he has published around 210 journals and conference technical papers on microstrip-based microwave antennas and components. He has 2 US patents and more patents are filed on leaky wave RF energy harvesting, circularly polarized grid antenna technologies. He has edited 2 books and contributed a chapter to a book, Microstrip Antennas, in 2011. His research interests includes multi-layered microstrip structures, millimeter wave antennas, RFIDs, GPS, UWB antennas, metamaterials, etc., and beam steering and beamforming systems. He is a senior member of IEEE and IEEE APS. He is awarded a senior research fellowship from CSIR, Government of India in Engineering Science, a discovery project fellowship from Australian Research Council, exceptional performance reward award certificate from IEEE Antennas and Propagation Society in 2019. He is an associate editor of the International Journal of Antennas and Propagation and various antenna, microwave, RF related journals, editorial board member. He has been member of organizing committees of several antennas and propagation related conferences and has serving as publication chair, publicity chair, and conference secretaries. Currently, he is the chair of the IEEE Singapore MTT APS Joint Chapter and publication chair of IEEE APS 2021 Singapore. So I invite Dr. Nasimuddin, a very good friend of mine, to deliver this talk, and I thank him for taking out the time and heeding to our request to give this talk. I hope all the participants will be benefited by his immense experience on the microchip antenna technologies. So I hand it over to Naseem. Welcome to you, Naseem.
Thank
What is yours now?
Ashutosh for very long introductions and invitation to be here. And I would like to also thank Bangalore IEEE section and AP-MTT chapter committee and Puneet and Mahesh. And good evening and good night everyone, and hello everyone. So today I am going to present the beam steering beam forming antenna technology, and I will share some view on this. Can you see my slides?
Yes, yes, we can see.
Okay, good. So the today's talk on overview of beam steering antenna system. As you know, nowadays the connectivity is very important, and we are going to 5G millimeter wave. So the beam steering antenna technology is very hot topic nowadays. And so today I will present some technology about beam forming and beam steering antenna technology. And today's outline of my presentation, motivation, why we need the beam forming antenna and what are the challenging and application. And I will discuss in detail overview on the beam steering, beam scanning antenna system and grid array antenna. This is something new technology for beam forming with low cost. And I will discuss some design. And I will discuss the beam scanning, or we call the frequency scanning leaky wave antenna. And I will discuss some new design, metamaterial or composite right left-handed structure-based leaky wave antenna. And I will discuss some potential applications for leaky wave antennas. And last not least, I will conclude and I will summarize this talk. So the motivation. So motivation of the designing the beam steering antenna system, the beam steering coverage should be wide and should be low cost and low power consumption and low weight. These are the four very challenging and very important for the beam steering antenna technology. So the power consumption and the cost is very important for the industry. How to reduce the power. So why we need the beam steering antenna. So connectivity is very important. Whether you are flying in the plane, or you are in the ship, or you are in the train. So you need to connect always with the satellite. So if you want to connect always with the satellite, you have to have the ReConfigurable antenna. Means your beam should be changed based on the speed or based on the plane speed. Otherwise, you will not connect the satellite. So if you have the high gain antenna, it means narrow beam. You will cover very small area. So if you are in the plane and plane is moving, so you need to connect always with the satellite. You need to connect always with satellite. So the beam steering technology is very important and key technology. So how to connect with unconnected? So the concept of the 5G have to for everyone, for everything, and connect it to everyone. So for connectivity, we should have the beamforming antenna, or if you want to the imaging system or tracking system and drone system, all we need the beam steering antenna system. The key technology is the beam steering antenna for all these applications. So there are the lot of applications: automotive radar, 24 to 77, navigation, tracking, and LEO satellite, inter-satellite communications, and SATCOM on the move, cellular communication, 5G, space system, drone, and the airborne systems. I just talked that if you are in the plane, you want to always connect with satellite, and you have to have the beamforming antenna. And imaging system and scanning and wireless power transfer system also need the beam steering antenna, because you can transfer the wireless power to the different sensors. And some application on RF energy harvesting, you can harvest the energy from the different direction if you have the beamforming antenna. So the connectivity, we should have the reconfigurable. The reconfigurable antenna is the three type: the frequency reconfigurable antenna, and radiation pattern reconfigurable antenna, and the polarization reconfigurable antenna. So the polarization reconfigurable antenna means you can switch the polarization like left hand, right hand, Nelian polarized, horizontal or vertical. Another type is the frequency reconfigurable. Frequency reconfigurable, we can design based on the like Reflector diode or the liquid crystal material. You know, the liquid crystal material, we can tune the dielectric constant based on the biasing. So you can design the tunable frequency antenna. The other part is the pattern and the beamforming reconfigurable. So this one I will talk in detail today. So the pattern reconfigurable means we have the switching beam, beam steering, beamforming, MIMO antenna, and there are the different type of antenna. So the connectivity in motion, so we should have the reconfigurable antenna system. You are in the train or ship or in plane, so you have to have connect always with the satellite to talk with your friend, or you want to watch the movie, or you have the meeting, so you need to connect with satellite. The connectivity is the main key. So there's the pattern reconfigurable. We have the switch beam or fixed beam. If you have the multiple feed feeding to the antenna, you can generate the beams. This is the switch beam or fixed beam. Another type of the beam steering antenna is based on the phase shifter. We call the phase array antenna, or we have the digital beamformer. And there's a two type of the beam steering antenna, electronic beam forming antenna. So if you add the fixed delay or time delay in the antenna, you can get the fixed beam. You cannot change because the fixed time or phase delays. And other is if you have the variable phase between the two antenna, you can change, or two or more antenna, you can change the beam by changing varying the phase between the phase delay between the antennas. So the phase array antenna based on the variable phase and variable amplitude. You can control the beam direction, beam shape, and others. The main beam direction depend on the relative phase between the antenna. If you like this, you have the relative phase difference and delta phi. Based on that, you can calculate the beam angle theta. So let's say if you want to get the 30 degree, so you should have the phase delay around 90. So this is the standard formula, and this is not new, and this is the phase array concept. And you need two or more antenna to design the beam steering antenna. So what is the requirement for the beam steering antenna system? So the beam steering requirement, the coverage should be wide enough to communicate with the satellite wherever you fly. You are flying anywhere, so you always connect with the satellite, or you have the wide coverage system, or you want to scan some like the oil pipe or the building, you have to have the beam steering antenna wider. And gain for the link budget, and the narrow beam for the improve the signal to interference and plus noise ratio. If you talk about the millimeter wave, so the free space path loss is very high. To compensate the path loss, So you have to have the high gain. High gain means narrow beam. So if you want to cover the plus minus 90 degree, so you have to have the beam steering antenna and high gain antenna. So the other part of the requirement is the cost efficient, low cost, and power efficient should be low power consumption. And for the satellite, the weight is very important, and the aeroplane, the profile should be very low because to reduce the drag. If a very high profile, then dragging problem other. And easy to use should be very not so complex, very easy to use. And the other requirement like simultaneous multi-beam. So you can connect with the simultaneously two users or two satellite like LEO Geo or MEO Geo or MEO LEO, and should multi-band and multi-polarize. Like if you want to use like one is the right-hand polarized, other is left-hand polarized, or vertical polarized, horizontal polarized, like, and multi-beam technology for 5G and other applications. So the type of the beam steering antenna system, the two type mainly. The one is the mechanical, and other is the electronics. We have the switch-based, phase shifter-based, digital former, analog, hybrid, and digital. So the other type is the lens multi-beam. Like if you have the different shape of the lens and you have the multiple feed, you can generate the multiple fixed beam. And Butler matrix, Rottman lens-based antenna array, you can generate the fixed beam. And other type is the transmit array. If you have the more feeder, you can generate the more beam, and you can have the some fixed beam. And I will discuss this part, the multi-port grid array antenna. This is some new technology we have worked on that. And I will discuss the frequency scanning leaky wave antenna. And other is very interesting beam steering technology on tunable material based beam steering antenna. This is very interesting. And other new technology, metasurface based the beam steering antenna system, and holographic beam. This is like a hologram based, like optical based beam forming antenna system. And other type is the conformal sector type, is very simple antenna beam. You can have the sector-wise sector beam in different direction. The mechanical beam steering antenna is very good. You can get the wide coverage without any scan loss or any side lobe issue, any grating issue. This is the best beam steering technology. But the problem is the heavy, bulky, and maintenance. And other very big issue is the slow beam scanning speed. This is the main disadvantage for mechanical beam steering antenna. Otherwise, mechanical beam steering antenna is the best because you can get the in all directions is the same gain and same side lobe and other thing. And other technology you cannot get. So this is the advantage for mechanical beam steering antenna. You have the wide coverage plus minus 90 and 360 degree you can get without any degradation of gain and side lobe, grating lobe. And this is the issue, only the slow beam steering scanning speed. Speed is the issue, big issue. The other is the electronics beam steering antenna system. The one of the is the cost, power consumption, and the complexity and the scan loss. You know the phase array antenna based on the microstrip antenna. The microstrip antenna have the limited the pattern. If you have the like this pattern plus minus 45 degree, so you can scan the beam within the 3 dB scan loss plus minus 45. If you go the minus 90, you have the more than I think around 15 dB loss. So the phase array beam scattering antenna depend on the single element radiation pattern. So beam is moving like this within this pattern. So it means if you are scanning minus 90 or plus 90, you have the 15 dB loss. So the electronic phase array based technology is the very good for fast beam scanning, and you have the accurate and positioning capabilities for electron beam steering system, and you can get the very good, very high beam resolution. This is the advantage. These three cost, power, and the complexity and scan loss, some side lobe issue, also grating lobe issue, or there are so many issues. You need a very big team to design the phase array. You need a signal processing, the circuit, antenna, and the digital, FPG, and so many things. So you need a very big team to design this one. So the cost is very high, complexity. So the electron beam steering antenna technology have the different type like analog RF and digital and hybrid. So analog, we have the one RF chain only, and digital, each element of the antenna have the RF chain. So you can generate the multi-beam simultaneously. This is the advantage. And other advantage of digital beam forming is you can generate the very fine beam resolutions, and you have the multi-beam, whatever you want 100 beam, you can generate the 100 beam. But the problem is the very high cost digital beam forming, because each element look like a transceiver. So you have the RF chain, this AD, DC, and converter, and so many things. So the power consumption is very high and cost also very high. The other type between the hybrid beam forming technology, RF and the digital combined. So this one has a little bit improvement in the cost and the power consumption compared to the digital beam forming. So you can generate the multi-beam this technology, but the overall the electronic beam technology based on the phase array or digital beam forming is the high cost and high power consumption, and this is the very important for industry. And in industry, there's the electronic beam forming antenna system. There's so many companies, but I just listed the whoever using this satellite and airborne antenna system. So ThinkPad and Satisfy and Phaser and JetTalk and Boeing, these are the leading antenna beamforming technology based on the phase array, conventional phase array antenna. So that this is the new technology generating in the world now. The Alkane is the new startup company, and K-Meta also use the metamaterial, means they use the liquid crystal combined with the metamaterial. Alkane also use the liquid crystal based phase array antenna, and the isotropic, they have some optical concept, and the pyovoltal is using the holographic method, and they are the Metawave and the Ecodyne. There's so many companies. They have the different concept to reduce the cost, power consumption, the two main issue they are going to solve. And we call this one unconventional electronic beam forming antenna. So if you look at the K-band dual circular pulse phase array antenna. So this is they use the IC chip to design the phase array antenna. You know, the IC nowadays very smart. We can design very smartly the phase array, and you can switch the right hand, left hand, and vertical, horizontal polarized is very smart chip. So you can see there the 1024 element. So each 4 element need one IC. You can there the so many IC you need to design the phase array, and there the other thing also the power, digital line, everything, FPGA. So this is the 32 by 32 antenna element. You can see here they can get the EIRP around 74 dBm at K band. The scanning is only the plus minus 30 with the XL ratio less than 3. And if you look, the scan loss is the 4.5 dB is very big. If you go the beam in plus minus 60 degree, you have the 4.5 dB is very big loss for system design. So this is the front view and this is the bottom. You can see the IC, there the IC, black color. So the concept is this, that you can see the one IC connected with the 4 antenna. So antenna have the one feed is the right hand, other feed is the left hand. So you can switch the beam in right hand or either left hand in the phasor antenna. This is a very good paper, recently published. So if you look the design, overall design, so they have the IC here, then the antenna layer, and the power line, control distribution line, feeding line, and this is the power divider, and this is the some digital line also. So the overall design, antenna element design is very complex. So need more than 14 layers. You can see here. So this is the just one element. So this is the axle ratio in the right hand, left hand, and this is the beam scanning. You can see if you go the 60 degree, almost around 4.5 dB loss. So this the IC and element connected here. You can see the right hand, left hand port, and you can connect. You can generate the circular polarized other way also. If you have the dual polarized antenna, you connect it with the IC. So IC can generate the 90 degree phase delay here, then you can generate the circular polarization here. So this configuration of 2x2 can generate the circular polarized and horizontal polarized or vertical polarized, and this is very interesting and can generate the right hand, left hand also. So if you have the dual polarized antenna element design, so you can generate the 4 polarization, vertical, horizontal, and the right hand and left hand circular polarized. So I see nowadays very smart. So we can design smartly the phasor antenna. So these are the some IC, commercial IC available in the market to design the flat panel phasor array antenna for 5G or satellite or airborne or other application. So these are the IC available in the market. So these IC can reduce the losses, cost, overall size, because the one IC have the everything, right? The transceivers, the transceivers and polarization switch, and low noise amplifier, power amplifier, phase shifters, and the variable attenuator. So the IC is very smart. So if you design the phase array with the separate components that look like a 3D. So if you design the flat panel like this is very flat. Only I think the 5 mm thickness of this overall 5 mm or 3 mm. So you can use these IC to design the flat panel very thin. Otherwise, the phase array antenna is very thick, 3D, like a 3D. So these IC, I think Anoki Wave is the commercially available. You can buy. We are using the Anoki Wave nowadays. These IC. So the one IC have the 4 port, right? This one. So you can connect the 4 antenna with the 8 port. So this one we have designed with the LTCC based technology. LTCC is the like a PCB technology, but is very expensive. But we can design very accurately the antenna, and we can get the very good performance. So we have designed this. We use the circular polarized wide beam circular polarized antenna element to get the wide coverage with the less scanning loss. Only if you scan the plus minus 45, we have the scan loss only 2 dB. And we can get the very fine beam resolutions, only 8 by 8, around 1 degree. And this is you can see this is the 8 by 8, and this is the antenna element, and this is the backside. This is the chip IC. We use the 4-channel IC and this IC wave. And the Fujitsu just demonstrated the one technology, multi-beam technology. They can have the 4 beam and for different users, and only use the 128 element and can get the 10 Gbps. So for 5G millimeter waves, so you have to have the multi-beam or beam scanning capabilities. So we can have the connectivity with the multi-users simultaneously. So the other type is the lens type. You know, the lens, if you have the different structure lens, you can be, if you feed lens in different location, you can get the beam in different direction. So based on this concept, you can generate the multiple beam, but is the limited space here, right? You cannot put the 1,000 of the element. So you have the limited space, so you can generate the limited beam only. Like this example, they use the 16 patches to excite this lens. They can get the 16 beam in 16 direction. So the issue for this type of the lens, the one is the heavy, bulky, and you cannot control the beam resolution, right? So is the limited. You cannot put the very tightly these patches. So then issue the mutual coupling other problem. The cost is low cost, and we can generate only the fixed beam because we don't have the any phase shifter. If you have the phase shifter here, then you can scan the beam and you can improve the beam resolution also. But then again the cost increase if you're using the phase shifter. So just connect with the RF switch. You can see here they use the single pole 4 through switch, RF switch, to control the 16 port. And the other type is the Rottman lens. You know the Rottman lens, if you have this is the physical structure, the lens type, like metal type. And then if you feed in different location, so you have the different time delay. You have the fixed delay in different feeding. And if you connect the antenna structure here, so you can have the beam, you can generate the beam in this direction. And if you connect the leaky wave antenna or other beam steering antenna here, so you can get the 2-dimensional beam scanning. Using the Rottman lens, you can have the in this direction, and by using the leaky wave antenna, you can have the beam scanning in this direction. So using the Rottman lens with the leaky wave antenna, you can get the 2-dimensional beam scanning with very low cost because there is no any phase shifter or other thing, right? So you can generate the 2-dimensional beam scanning capabilities based on the Rottman and the leaky wave antenna. So the concept in this paper, in the 2 reference, is very good reference. Their concept to have the multiple element in different angles, in the paste in different angle. They can use the in aeroplane to have the beam in different direction. You can switch the beam in different direction, right? Like the fly. So this is also very low cost solution. Only the you need a very large. This is a very large footprint for Rottman lens. The other this is the one of the application of the Rottman lens. I think recently published last year and Scientific Nature journal, and they use the Rottman lens for energy harvesting for millimeter wave at the K band. So they use the Rottman lens like a 8 beam in different direction and connected with the rectifier and the RF combining and then DC combining. You can see here the rectifier, DC combining, first RF combining and then DC combining. So they can get the major voltage around 6 volt and different at different power densities. So they use as a power grid. They call the power grid, and they have some patent also. They the very good. Very good application for Rottman Lens using in the energy harvesting. And other type is the butter matrix. The butter matrix also can have the beam, switch beam or beam steering in depend on the butter matrix size, like 4x4 you can get the 4 beam, you have the 8x8 you can get the 8 beam. So if you want to cover like scanning or using for power transfer or some other very low or receiving application, you can get you can use the butter matrix very good. But only the problem is the footprint side, very large footprint. You need a 4x4 butter matrix, 4 beam. You need 4 hybrid coupler, and you need crossover and delay line, right? So the overall structure, you can see this structure is very large. And this is the butter matrix antenna is this part only. So the overall structure footprint is very large. So the beam direction depend on the theta and the distance between the element D and this delay. So the 8x8 butter matrix, you can see they can cover the -90 to +90. You can see the almost -60 to +60. You have the very good beam gain right here. So the for some scanning application or some tracking application, you can use the butter matrix is very good low cost solutions. And the application of butter matrix we have used for one concept just for a student project. We designed the butter matrix very compact size. You can see the 4 this is the crossover and this is the 4 hybrid coupler. Very small, and we have the 4 antenna very compactly get the angle in different to power up the different location sensors, and we can get the beam in the -5, 65 angle, -45 and 20, and with different feeding port. If you connect the RF switch in the butter matrix, you can electronically switch the beam in different directions. So this is the one of the example, and then you can use for the energy harvesting also this concept. So other type is the blast matrix, also can have the same concept like the butter matrix, can have the beam, fixed beam or variable beam if you have the phase shifter or some material type. So this one also need the hybrid coupler, and the footprint, overall footprint is very large. The other type is the transmit array type. You know the transmit array, we can design the flat type. If you have the multiple feeder, like here the 4 feeding here, so you have the 4 beam in different direction. Like car radar 77 only need the ±17 degree scanning. So it depends on the multiple feeder. If you have the more feeder, you can design the you can generate the more beam. And if you have mechanically tuned this feeder, you can tune the beam in the transmit array. And RR is the reflector array, same concept. You have the multiple excitations, you can have the multiple beam. This technology very low cost, only the problem is the bulky and heavy. And the reflector antenna also, reflect antenna also have the same concept. You have the multiple beam, you can get the multiple excitation, you can get the multiple beams. And again is the heavy and the bulky. So the other is the simplest one is the sector and conformal antenna. You have the antenna, high gain antenna in different direction. You can switch the beam in different direction like this. You can switch the beam based on the sector by sector using the switching or other. So the technology, the holographic beamforming antenna technology, they claim the size is very small, low cost and low weight and low power consumption. So they use the Reflector diode, and each element connect the Reflector diode, and based on the manipulating the biasing state by the smart FPGA or other software, they can like software defined radio or something other technology, they can generate this technology can generate the beam in the desired direction. And you can see that just comparison phase array and this holographic beamforming technology. So they claim they can reduce the power consumption around 3 times with the almost same gain and other thing. So the main challenge, they are working for the reduce the cost and power consumption and weight size. And the other is the metamaterial based electronic beam steering technology. The low cost, this technology low cost, you know, the K-meta, they use this concept K-meta, and I think one of the author of this paper. And the size and weight and power consumption they can reduce, and they use the Reflector diode with this is the unit cell. You can see this is the Reflector diode they put in the both sides, and they use like a planar linear array using the SIW concept. This is the SIW, and this is the transition CPW to. So they one direction they use the phase shifter, and other direction they use the Reflector diode. They just tune the voltage, and the Reflector diode change the capacitance, means you have some delay. Capacitance means you are changing the effective dielectric constant. It means you are changing the delay. So based on this, you can generate the delay by switching by biasing the vector diode. You can see here the phase is changed by changing the state of the by changing the biasing. So based in this concept, they can generate the beam. They can steer the beam in different direction. So this is the prototype. You can see and they have the number of the like the planar leaky wave antennas, and they can steer the beam in both directions and the elevation. Only the issue is if the azimuth is the scan loss is very high compared to the elevation. Other problem is the efficiency. If you look, efficiency is very low, the 8% or only 8%. Side of okay, 10 minus 10 dB. But if you look at the directivity, 20, the gain is less than 10. So this type of antenna, because they use the Reflector diode at the 10 gigahertz, 10 gigahertz the lossy. So that's why the efficiency is low. If you're using this technology at the low frequency, 2 gigahertz, 4 gigahertz, I think should be okay. So other is the very interesting. I think this is also a very hot topic nowadays. People working in this, they call the digitally controlled metasurface. So the metasurface, this is the unit cell of a metasurface. If you have the diode in between this line, you can change the phase like 1 0, like this is the 1 bit. They call the 1 bit metasurface. So you have the off and on. So based on the off and on, you can change the phase delay, right? You can see here the phase difference is the 180. So based on the state 1 0, you can have the phase change. So you can see the on and off, the pattern is different. So based on this concept, so metasurface can be designed in different pattern, like 0 0 0 and 1 1 1, like this pattern. Based on this pattern, you can generate the beam. If you excited this surface, You can generate the 4 beam, or if you have the different pattern, you can have the different angle 4 beam, or you can generate the 2 beam also, and depend on the pattern of this 0011 pattern. So they have verify experimentally, and they have a design, and they connected to the biasing. And if you have the biasing very smart, and there are some other paper also, you can tune the beam based on this. Some smart software by manipulating the biasing state of this diode. You can generate the beam, and you can scan the beam. It depends on the how smart you are changing the biasing. So other is the 2-bit. If you have the 2 diode in the one single metasurface unit cell, you can have the 4 stages: 1 0 0 1 1 1 0 0 1 1 0 1 1. So you have the 4 stages. So based on the 4 stages, you can generate the multiple beam. So you have to very smartly thinking the pattern, like 0 0 1 0 and 0 1 1 1, how to beam in different directions. This paper is very interesting paper for the metasurface, and they have fabricated and verify experimentally, and they have verified the 2 cases. You can see the 2 beam here and 4 beam here. So these are also very smart technique to generate the beam in different direction based on the. So this is the material based. If you have the liquid crystal based electronic beam string, this is a very interesting design. They use the liquid crystal as the substrate. So you can see this is the element, and this is the feeding line here, and this is the liquid crystal here. So if you buy the liquid crystal, you can change the dielectric constant of this layer. So based on the change the dielectric constant, and this spiral create the delay. So based on this delay, because you can control this biasing very fine, so you can generate the very fine delay. So the beam resolution can be very fine, based on the how to control the biasing. So based on the biasing, the liquid crystal dielectric constant change in the liquid crystal dielectric constant, you can create the delay. So based on this concept, you can have the beam in different direction based on the changing the biasing. So they have verified this concept in this paper, and then they have patent, and now they have the startup company called the Alkane system, antenna system in German. And this year, I think they are going to launch the phase array system based on the liquid crystal in the space. And this just some results. So based on the changing the biasing, the beam can change. You can see here, image change. So they have the product in the market now, I think, for the receiving and transmitting both band. This is the antenna size, very small size, and they claim they can reduce the cost 5 times and the power consumption around 5 times. So this is the advantage for this technology, and only some disadvantage. Till now, they don't have the flexibility, because they cannot change the polarization, right to left or vertical to horizontal. This is the only I think some disadvantage. Otherwise, this technology is very cheap and very low power consumption. So now I will discuss the grid array antenna technology. So you know the grid. Each grid antenna is grid designed based on the frequency. So this grid length is the lambda g, and the width, this width is lambda g by 2. So based on this number of the grid element, you can design the structure, and based on the feeding, you can have the multiple feed in the where the current is 0, like this node and this node. You can add the multiple feeding. So for demonstrations, I have added the 9 feed in this structure, port 1 port like this, and we don't have any phase delay or any phase shifter in this system. Very simple. You can see only the one dielectric layer, and this the grid array antenna, and we have the feeder. So based on this feeding location in different place, we can generate the beam in different direction. You can see here the 9 feed, and we have the beam in the 9 beam in different direction. So this is technology very simple and very low profile and very smaller footprint. You can only just this footprint, and we have no need any like butter material. We have to have the hybrid coupler, crossover, phase delay, or like this. So that this structure only need the multiple feed in the different location of the structure. You can get the beam in different direction. So this is very interesting for researcher to get the very low cost beam steering antenna for simple application. So you can, if you look the electric field distribution based on the location, if you have the feed here, so that you can see the electric field, the majority in this direction. Based on the feeding, you can see in this direction feed. So if you feed in this direction, if you have the center, you have the majority of toward in the center, like this. So the location of the feeding change the beam in the different direction. So you can see the beam here, right? And the different direction beam have the, you can have the like horizontal, the diagonal direction. You can see the 4 diagonal direction beam. If you feed here, you can get beam here this direction. If you feed here, you can get this direction like this. So these are the 9 beam. I just put the nine feed. We have the 9 beam in the different direction. So this is very simple technology. Just need to add the RF switch to demonstrate the electronically hit the beam. So for simple verification, I just manually measure the feed one by one. You can see the very good agreement, simulation, and the measurement in the all beam, like this direction beam and center beam and this direction beam. This is the other direction beam. You can see the very good agreement between the measurement and simulation. So we have verified this technology, and this is very simple, very low cost. Need just to RF switch to control the beam. So next I have demonstrated to connect the switching network with the 9 feed. You can see the 9 port here backside. This is the fabricated structure 9 feet, and this is the switching diagram. So based on this is the RF in here. So RF in here, and then this is the switching control. So based on the switching, we can generate the beam in different direction. So this one we have verified, and we have the beam in different direction, P11 and P3. Means this direction beam have the same angle, around 20 degree, and P31, P13 in this direction beam almost same like this, around 20 degree, and this direction P12 and P1, the beam in the around 15 degree, and P21 and P22 and P23 beam can generate in the with the center beam P22 at color. So we have demonstrated the electronically based on the RF switch, we can generate the beam in different direction, very cheap and very low cost and very simple structure. So this is a very interesting for researcher also. Still research ongoing in this. There are some issue, still issue. So we have also verified this structure for circular polarization. So we just added the one polarizer on top of this, like circular metasurface polarizer. We can generate the circular polarizer at 93 gigahertz. You can see the beam, three beam. We have used only the three feed. We use in this structure a coplanar feed here. We excited the three different location. So we have the three beam in different direction. One, this is the center, and this is the axial ratio at the beam direction is the below 3. We verify we can generate the circular polarization also using the grid array antenna technology. So the next topic I will discuss the leaky wave antenna. Leaky wave antenna, you know, the leaky wave antenna is very simple antenna. This is the transmission line structure or traveling wave type structure. And the wave leakage from the structure gradually in the free space. And the beam depend on the beta, the frequency dependent, the direction of the beam. So if you look the conventional leaky wave antenna only scan beam in the forward direction. So there are the different type of the structure, the uniform, non-uniform, periodic, non-periodic also there. So the beam angle depend on the beta, and the beam shape depend on the attenuation constants. If you have the like taper, you can change the beam, you can change the beam shape based on the short or the uniform or tapering or unperiodic or like this. So there's a lot of research in technology. So the leaky wave antenna, if we use metamaterial, we call the composite right left-handed transmission line based leaky wave antenna. We can generate the beam from backward to the forward direction along with the both sides. So the right left hand means we have to have the some left hand transmission line and the right hand. Then we can design the composite right left handed transmission line. So based on this transmission line, we can design the leaky wave antenna, which can generate the beam from backfire to the fire with the both side. Both side radiation we can generate only when the right hand region energy equal to the left hand region. So we can generate the both side region. So like this, green one is the left, red is the both side, and the one is the forward direction. So we have to have and this is the normal transmission line like microstrip line, and this is the left hand. So for left hand we have to have the series capacitance and shunt inductance. So the main task for this left hand, we have to create in the normal transmission line, we have to create the series capacitance and shunt inductance. So we can design the right left-handed transmission line. So based on this transmission line, we can design the leaky wave antenna, which can send the beam from backward direction to the forward direction. You can see this is the circuit diagram, just now. So the left-hand transmission line, we can scan the backward direction, and right-hand transmission line, we can scan the beam in the forward direction. So in the black color is the balance condition. We can generate the beam in the both side direction. So this is balance condition very satisfied because this is the very frequency dependent. So when the condition satisfy, the series and shunt resonance is equal. So this is very, very sensitive and very, very narrow band. So this is the challenge. And other challenge is how to design the same bandwidth, left hand and right hand. These are some challenges. So for designing these CRL transmission line based leaky wave antenna, we use the SIW technology. This is the SIW. You can see the wall, via wall, and this is the slit. So we can generate using this slot and this parasitic capacitance, the parasitic patch. We can generate the series capacitance, and using the this via, we can generate the shunt inductance. So in this transmission line, we can add the shunt inductance and the series capacitance using this slot and this parasitic patch between the slit and ground plane. So you can see this cross section view. This is the slot, and this is the parasitic patch here, and this is the ground plane. So we can generate the capacitance here and the inductance. This is the concept. So this is the 1 unit cell. So we have the number of unit cell. If you have the more number of unit cell, you can have the higher gain. But this is if the leakage very small here, you cannot get the. If you further increase the number of unit cell, you can not have the very high gain. Cannot have the gain increment. So based on this, you have the composite transmission line unit cell. And you have to check the dispersion diagram. This is very, very important. Get this diagram, you can get the CST or other theoretical method also. So you can see here, this is the beta. If you have the beta 0, you can have the balance condition. So at around 9 gigahertz, you can get the both side radiation. So this is the left-handed region, and this is the right-handed region. You can see the left-handed region is a narrow band, and right-handed is a wide band. So how to make this equal? This is also one of the challenge, and the other challenge I will talk later. So we have simulated. You can see we increase the number of unit cell. So this is the 1 unit cell, right? So we change the unit cell like 5 to 35. So from 5 to 15, the gain change drastically, right? 5 to around 12 to 13. After that is gain change very slowly because the leakage going down. So you can see here also, if you have the number of the unit cell 5, the gain is around less than 5, and if you have the 15, the gain change. After that, if you change the 25, gain not so much change. So from 5 to 15 is the drastically change. So that's why we use in our study, most of the study in the 15 unit cell. So this is the gain with the beam scanning. You can see this is the beam scanning angle, and this is the gain. So you can see from minus 75, we have the very good gain around till this plus 75. So it means you can scan from minus 75 to plus 75 with gain around 10 dB. So the other challenge, how to make this graph like beam scanning with frequency linearly. This is also challenging part for leaky wave antenna. If you have the linear this scale, so you can simplify the system design. So you have the linearly scan the beam with frequency. So this is the beam, the simulated radiation pattern in different frequency. You can see the 8.2 with the left hand, and 9.5 with the right hand, the 8.95 the both side. You can see the beta 0 is the slightly less than 9. So this is the frequency is the 8.95. So this is the just radiation pattern, 3D radiation patterns of the leaky wave antenna. And then we have fabricated and measured. You can see the very good agreement between the measurement and the simulated, and the beam scanning angle versus frequency, and the gain versus frequency, very good agreement. They're just as parameters. So you can see the left-hand region with the measurement and the simulated radiation patterns, very good agreement. And this is the board side, and this is the left-hand region. Right-hand region, you can have the forward direction. So other problem for leaky wave antenna, you can see the beam width. Beam width is changing with frequency also. This is also one drawback. And then this is also one very good topic, how to make the beam width the same with frequency. This is also. So there are the three challenges: how to make the left hand and right hand same bandwidth, and other one how to linearize the beam scanning with frequency, and third one is the how to design the consistent beam width with frequency. So the next one we have used a dual composite right left-handed wave structure to enhance the both side radiation bandwidth, because we want to the some wider bandwidth at the both side, because the balance condition very narrow band. So if you have some design problem or other things, so the balance condition can be out. So if you have the wider both side radiation, then we can use this antenna. So we use the same concept. You can see that we have the dual unit cell. The one unit cell, we have the slot and the parasitic patch here. So the other structure, we can also use this parasitic patch on top of this. We can also get the same performance, slightly same performance. So just think how to create the series capacitance and shunt inductance. So we have some comparison with the dual and the single. You can see this is the both side radiation with frequency. The dual can enhance the both side gain. Both side gain bandwidth. You can see if you the 1 dB gain bandwidth is the wider compared to the single wave antenna. So the single leaky wave antenna only the 175 bandwidth, 1 dB gain bandwidth, and dual have the just double 75. So we have again studied the number of unit cell, and the other we have studied this slanted and the rectangular. So the 45 degree is giving the very good both side bandwidth. You can see we have the other combination 0.15, 0.30, 0.45, 0.60. The best one is the 0.45. So we have to use the slanted combination, rectangular slanted combination. And then we have fabricated and measured. You can see the very good agreement, measured and simulated. This is the both side only, the both side radius. And we have also checked the maximum gain in all directions. The other one, we have also measured the beam width with frequency and beam scanning with frequency. You can see the beam width, the narrow, the left-hand region. This is the left-hand region, and this is the right-hand region. So left-hand region, the beam width is wider, and right-hand region have some consistent of beam width. This is the issue, how to design the consistent beam width in region also. So this is the just major radiation patterns in the left hand region. So you can see the beam in this direction, and this is the both side valence condition. You can see the beam in from 8.8 to 9.1. We have the in both side direction. So in this paper, in this work, our focus to increase this both side radiation. So we can get the wider both side radiation compared to the single antenna. And this is the right hand region. So the other one combination, we have used the rectangular. This is not so good compared to the slanted and the rectangular one combination. So we just fabricated and verify this. And the other one, we have used the taper unit cell. The different, this section is the smaller slot. You can see the slot length. And this section has slightly wider, and this one the widest, the largest one. So that this concept also we use to enhance the both side radiation bandwidth. So this concept, same structure we use, only just using the taper like this. So we can enhance the beam width, the bandwidth of the both side radiation. You can see the gain reduced, but we have a wider both side radiation. We have just verify experiment and simulation. And these are the measurement result. This is the beam scanning with frequency, very good agreement. The beam width. So beam width is changing with frequency, and this region is the consistent beam width. And these are the major radiation patterns in different measured and simulated radiation patterns in different region, left hand region, balance region, and this is the right hand region. And again, we have used the same concept to verify this one again. So we use the like smaller, larger, like this. Different concept also work, and it is good. And we have enhanced the both side radiation band. We have measured and verified with. You can see the beam in the both side direction with different frequency. And for our target to how to improve this graph, but it's still not linear, but slightly improve based on the using the dumbbell shape plot and keep the other structure same. We just to modify this plot shape. We have enhanced this angle with frequency slightly enhanced, but not still need to work on this. How to get the linear graph with frequency. This is also very challenging. We have verified with simulation and measurement. Good agreement with measurement. So this is the challenge, the motivation how to design the linearly scanning with frequency. So the one of the student working on this, and she designed very smartly unit cell. This is the unit cell. She used 3 metallic via here, and the simple structure, single layer, no need any parasitic and other thing, simple layer, and I think slightly almost same bandwidth, in both regions. This is the air line and this is the dispersion diagram. And you can see the phase is 0 here. The bandwidth with both region almost same, not big difference. And these are the some dimension, and this is the structure. So we use the 15 unit cell to design the leaky wave antenna and check the performance. You can see this is the gain with frequency, and 24 to 32 we can use this leaky wave antenna, and this is the beam in different frequency. The one is the very interesting, and she achieved the almost linear graph of the beam scanning with frequency from 24 to 32 or 34, so almost linear scale. So this is a very good design, but we have not fabricated yet. This will be, and so I think this is very good. Can simplify the system design based on the linearly and beam frequency. So other paper in the literature, they have used at the terahertz for scanning or imaging purpose. They can also get the very linear scale with the frequency scanning. You can see this is the beam, the frequency, almost linear scale. So they have used very complicated structure stacking of the patchy dielectric line. So many things. But the other important thing for they can get the very nice beam in both region, right hand region, almost bandwidth, beam width they can control different. So this is also very interesting design to get the scale of the beam scanning. So other one we have designed some antenna on the millimeter wave for 60 gigahertz. And this antenna we have verified to detect the crack on the metal pipe, crack around 1 mm. So we use this leaky wave antenna as a sensor to detect the corrosion crack on the metal pipe, even the pipe in the with the insulated layer. If you have the pipe and then insulator layer, and then we can detect the crack in the pipe. So we have the patent file of this structure with the whole system, and we have also this technology license in the. So the other design we have used for car radar 77 gigahertz, because car radar need only the plus minus 17 or 18 degree. So this antenna also can be used for car radar. So the other antenna in the literature, they use the multiple antenna for generate the multiple beam at the fixed frequency. This is also very interesting, because you have the leaky wave antenna, the composite right left-handed, and you have the 4-port. If you switch the port, you can get the beam in the different direction. So if you have the slightly the two antenna with slightly the lens condition frequency, and if you have the 4 feed, you can get at fixed frequency, you can get the beam in different direction. So this antenna can get the beam plus minus 17 degree. You have the feed is the combination of the switching the port in the different, like port 1, port 2, port 3, plus 1 and 3, and like this. So they can generate the beam. So this is also very simple structure. And for car radar, other application, you can use this kind of technology very simply. And the other one, and they use the butter matrix, 8 by 8 butter matrix. You can see the 8 port and 8 output port here. And they connected the 8 leaky wave antenna, composite right, left-handed based leaky wave antenna. So the leaky wave antenna is scanned in this direction, and the butter matrix, 8 Butler matrix beam can scan in this direction. So we have the 8 beam in this direction, and then frequency scanning in this direction. So this is the dispersion diagram at around 11 gigahertz. They have the both side radiation right, left hand region and right hand. So also the almost same bandwidth. And this is the unit cell circuit diagram. You can see the capacitance and the shunt inductance. And this is a very simple structure also. Other very interesting for leaky wave antenna, they use the vector diode. You can see the vector diode here. And if you change the biasing, and you can change the this we call the balance condition in different frequencies. Since from 2 gigahertz to 4 gigahertz, you can change the beam at the board side at fixed frequency based on the this biasing condition, biasing voltage. So you have the different biasing. You can change the capacitance, means you are changing the balance condition. So based on that, you can get the beam in different directions. So you can see here plus minus 60 degree you can cover at the same frequency based on the biasing voltage. This is also very interesting design, very simple design. You just need one biasing connect with all vector diode. You can see that this is the unit cell, each unit cell has the one vector diode, one biasing. And other one is the based on the liquid crystal based electronic beam steering of the based on the liquid crystal leaky wave antenna. So this is the cavity. They fill the liquid crystal here and then put the unit cell based leaky wave antenna. The fabricated structure, you have a cavity, then slot, and then the biasing line, and put the biasing, you can get the beam in different directions. This is also very interesting design, but one issue is how to get the proper liquid crystal material and get. And other one, we have just some student work verify the liquid crystal based array antenna by changing the liquid crystal dielectric constant. Can have the beam in the different frequency. So you can tune the frequency from liquid crystal and other things, and you can have the very wide band. You can cover from 24 to 40 gigahertz, all 5G band you can cover with the gain than 9 dB. And if you look at the only way both side, you can cover 34 degree or 34 gigahertz to. So based on the liquid crystal, we just fabricated simple without biasing, just for verification. So this is the cavity, and fill the liquid crystal here and put this one top of this, and this is the top view. So we can put the biasing here. So this is a very simple design for verification. So now I will discuss the application of the leaky wave antenna. So there are so many applications. So we can use the frequency scan leaky wave antenna for tracking, because we know the direction of the beam based on the frequency. So based on this concept, we can track the any object or any human and or other thing. So this is a very simple solution. So no need very expensive beam scanning antenna for tracking and everything, because we know the beam direction based on the frequency. So system, I think, can get the each location based on the frequency where the target or where the human, like this. So we can use the tracking the human or target any other thing. So this is a very simple and very low cost solution for targeting, tracking. So other is the imaging and detection. So if you have any metallic part or another thing, you can use the leaky wave antenna, because leaky wave antenna can scan the frequency like this. So like in airport, you can scan in the one go, like just too fast, the leaky wave antenna. So other is the gesture sensing. Because this leaky wave antenna is very sensitive, because beam is very narrow and a very directional beam. So you can use for sensing purpose, gesture sensing, hand gestures, and very sensitive antenna. Another one is the like imaging. So you have the dual metasurface based leaky wave antenna and in say the two sensors, so you can get the in two direction image. So you can have the some fast imaging based on this scanning. For the in one go you can scan the whole surface. Other direction you can get very fast. So we can using the leaky wave antenna, we can enhance the speed of the scanning, and this is our one of the patent we have filed based on the we can enhance the scanner speed almost double, more than double, because the one go the antenna can scan the large surface. So other is the tracking radar, and it can detect the cells and other object, moving object, where can be used this antenna for tracking the vehicles and moving objects. And some imaging. I just discussed this antenna can speed of imaging, because one direction you can like the vertical can use the leaky wave antenna, the signal processing, so that you can speed up the scan time faster. So I can summarize now. I think I have presented and discussed the various of the beam forming, beam steering technology, and I have discussed in detail the grid array antenna system for application of the beam steering or beam switching application at millimeter wave. And I have presented the various type of the composite right left-handed leaky wave antenna based on the SIW technology. And I have also discussed some challenging of the leaky wave antenna, how to design the linear scanning with frequency wave antenna. I discussed a lot of applications. So thank you everyone. Now time for hello, Ashutosh.
Yeah, I'm here.
Okay.
So I was just going through the chat box if any questions are there. Anyway, Mahesh, any questions?
No, sir. I think I request all the
Okay.
participants to type in the questions in the chat box.
Anyway, I have one question. Beamforming work is quite impressive, all this leaky wave stuff. So, but this liquid crystal thing, are you able to standardize the fabrication part of this realization part?
No, no, I have everything. I did everything, but the problem to buy the liquid crystal is very not easy because only one, two company have the liquid crystal for millimeter wave or RF application.
Mm.
So that there the some we have to sign the some form. So we our institute
Okay.
cannot sign some the
Okay.
material agreement form. We cannot sign. So this is the issue. But
So is this?
I think in India,
Hmm.
I have searched in India, easily you
Okay.
can get, easily you
Is
can get.
it?
Yes, because I
Okay.
check and I call them, so they say we cannot give to the other country, and only the
Uh-huh.
India. Yeah.
Okay. Okay. Just share that context here because I was thinking. So main advantage of LCP is the lightweight and the flexibility, right?
There are so many. So I think the LC is very good, but the only the problem to get the proper LC.
Yeah.
Otherwise, very good because I have done lot of theoretical work and I have some patent also, file patent. But to need some verification, I have not. Still, I am searching the vendor.
Okay.
There's a
Maybe we
some
can.
there's a some vendor in the China, but I have bought it, but material not good quality.
Okay. And moreover, this uh, leaky wave stuff is very good for low cost scanning applications. But
Yeah,
I
yeah.
was thinking from our phased array radar point of view, like such a wideband, if you have a wideband application, then it is okay. You can have a scanning for like 120-degree over like 6 to 7 gigahertz of bandwidth. But usually, this our pulse radars are not so wideband; they are very narrow band, like 1
Narrow band, yes.
gigahertz, less than 1 gigahertz. So there, I think this technology will not be so helpful, right?
For I think the problem for leaky wave antenna is the simple structure, right?
Hmm.
If you have the even the narrow band, you can use. For millimeter wave, we have used only for 2 gigahertz. Is working very good.
Yeah, that's right. It's good for the millimeter wave, but I'm like talking about somewhere up to X band.
X band, I think the structure size will be large. Yeah.
Yeah, structures, and I have done some work on this LWS as I discussed with you. I've seen that in X band, you cannot get the scanning more than like plus minus 20-degree to 30-degree maximum. That's what you can get.
Okay, okay.
But yeah, if I move the stuff from like 8 to let us say 18 gigahertz, yeah, then I can get that kind of wide scan.
Yes, I think the if you can solve the issue, right, like wide the consistent beam width and the linear beam scanning, right? Then I think you can use this antenna very easily, leaky wave antenna.
Yeah, yeah. But there's a lot of work going on around the globe. Yeah. I
Yeah,
can see
yeah.
that.
Nowadays, everyone working on the beam steering, beam forming antenna. But if you're designing the phase array antenna, I think very very complex. You need expertise, the big team, and other things.
Yeah, that's right. That's right. We have a very big team in India working on this phase
And
array.
if you're designing leaky wave antenna, single-handed you can design.
That is true. That is true.
And the cost, I think, is
So,
the very very important cost and the complexity, the
mm,
power consumption also, I think, because I discussed a lot of company guy here. The main challenge, I think, they discussed how to reduce the power and the cost. The two is the very very important.
okay. Power, you mean like for high power application, that's not suitable?
No, 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 no. If you look at the phase array antenna, you need the power consumption, right?
Yeah, yeah, yeah. That's right. That's right.
This is the other problem, other big problem for this IC I just presented, right? You need the
Yeah.
heat sink, right? Yeah, if
Yes.
you have, yeah. Otherwise, the IC is gone. If you don't have the proper heat sinking,
Yeah.
yeah, then this is a lot of challenges. I think in the 5G millimeter wave, lot of challenges.
That's right. That's
So that's why the all
and it,
company looking the low cost solution. still is not in market.
Yeah. Well, there's one question, like one person is asking, are simulations sufficient to substantiate your design with measurements? How much accuracy you get in measurements and simulations?
I think for leaky wave antenna is very good. And the other one I have presented, the grid array antenna, also very good, because very simple structure. And
Yes, that's right.
only the problem and the balance condition is sometime I think you need very fine meshing in the, if you are using the HFSS or CST, and you have to check very fine meshing. Meshing is very important.
Oh, and typically, how much is the simulation time involved for such designs? Is it computationally intensive or like simple structures too?
This one, because this it depend on the, if you have the single structure, right, single layer, then very fast. If you have the multi-layer, then you need around 1 hour, 2 hour.
Okay. Anyway, I'll get back to you off the line. Any questions, Mahesh, or shall we? I think we can call Puneet
Yes.
to.
Yeah,
Thanks.
yes, sir. Yes, sir.
Puneet is there, right? We can.
Yes, I'm there. So
Yeah, yeah.
before closing, I would also like to ask one question, Dr. Nasimuddin.
Sure.
During this your steering beam, you have shown that steering losses are up to 4.5 dB.
Yeah.
Don't you think this number is on the higher side, and what are there some development happening, and how we can reduce?
I
Because
think this one going, research is still going. I am also working. If you design the element is wide beam, right, then you can reduce this loss. Like if you have the radiation pattern like this, a hemisphere, you can get the this less number around within 3 dB. So this is a very challenging research and very
yes,
demanding also. Very demanding also. Because if you have the 3 dB loss means you have the double, right? Power double.
yes, that's what.
Yeah, yeah.
That's why
4.5 dB is quite large number. Yeah.
all system designing looking this solution, how to reduce this one. So the only the solution you have to have design the antenna element with wide beam. Is not so easy at the millimeter wave, because the other problem the phase array antenna design, you have to have the inter element spacing less than or equal to lambda by 2. Otherwise you cannot get the wide scanning.
Correct.
This is the trade-off between the wide scanning and the gain. And if you have the interspacing less, then you reduce the gain. And for 3 dB for such a big array antenna, you have very big loss. Means you have to double the antenna size to get the 3 dB loss.
Yes. Thank you, Dr.
This is
Nasimuddin. Thank you very much for your wonderful presentation. And I can see that a very exhaustive material is being compiled by you and shared with all of us. I think our attendees
because
and delegates who are
I just
joining
want
this.
to add one thing. I am a bit sleepy because my sleeping time is the 9 o'clock.
Yes. We will close. So I'm also running short of another meeting I have to attend. So anyway, thank you very much, Dr. Nasimuddin, for wonderful lecture. And
Thank you.
definitely we are going to upload this video in our YouTube channel, and those who are willing to revisit this, definitely they can see it. And once again, thank you very much for joining us and providing your wonderful perspective and sharing your knowledge. Thank you very much.
Thank you very much.
Thank you, Nasim. Good night.
No problem. Good night. Okay.
Good night. Bye bye.
Good night. Bye bye.